Okay, the last topic in this section is instantaneous rates of change. Earlier we said that derivatives can be used to find slopes of tangent lines, slopes of functions, or instantaneous rates of change. So the work here is not any different than what we've already done. It's just a slightly different context. So um, the most common example of finding an instantaneous rate of change is dealing with position and velocity. If you're given a function where if you're given a function that tells the position of an object, then you can take its derivative and find the um, velocity of an object, the velocity of that object. And this was actually how Newton got started when he developed calculus back in the 17th century. This is kind of interesting. Um, Newton, this is from the Wikipedia article. This is the part that I want to look at right here. After Newton finished his BA degree, the university he was at temporarily closed because they had the Great Plague. And so Newton had to go home for a couple of years to avoid the plague. And while he was at his family home, that's where he developed calculus and also the law of gravitation and optics. So that's also where the apple tree was that he supposedly sat under. I've heard that there really was an apple tree there, but looking at it is what gave him the idea for gravitation and not an apple actually falling and hitting him on the head. So let's look at this example. A rock is dropped off of a building that's 100 feet tall. The height of the rock after t seconds is given by this function. Find the instantaneous velocity of the rock at t equals 2. All right, well, to do that, really what they're asking us to do is find f prime of 2. And so that's going to be the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. So what I want to do is come over here to the side and work out what each one of these things is. And then we'll sub those back in. All right, so f of 2, that's 100 minus 16 times 2 squared. So that's 100 minus 64, so that's 36. I'll put the units on it over here. 36 feet. After 2 seconds, the rock is at a height of 36 feet. All right, f of 2 plus t, I'm going to do that over here. I'm sorry, 2 plus h is 100 minus 16 times 2 plus h squared. So you square that out, you get 4 plus 4h plus h squared. And if you distribute that and put things together, you get 100 minus 64, so that's 36, minus 64h minus 16h squared. All right, so if we take those two and then put them together back into this, we get f prime of 2 is the limit as h goes to 0 of f of 2 plus h, we worked that out to be 36 minus 64h minus 16h squared minus f of 2, which is 36, all over h. Now, derivatives, if you do them right, if you don't make any algebraic mistakes, then everything that doesn't have an h in it is going to cancel away. So we do that, and we're left with limit as h goes to 0 of minus 64h minus 16h squared over h. Now we still can't plug the 0 in because it'll give us 0 over 0, but we can cancel now. There's an h in every term, so I can cancel that out and I'm left with minus 64 minus 16h. I could put over 1 if I want to, it doesn't matter. Now I can plug my 0 in though. If I plug in 0 for h here, I'm just left with negative 64. My units there are feet per second. So that's the speed of this rock at t equals 2. It's going negative 64 feet per second. Makes good sense that its velocity is negative because this is talking about height, and its height is changing in a negative fashion. So if you want to look at that, let's graph it. I've already got it graphed out over here. 100 minus 16t squared. It's kind of hard to see. Let's make the x-axis go only from let's make it go from, say, negative 2 to 4. All right, now I'm going to adjust it a bit more. But yeah, so our rock is up here on the function, or it starts out with a height of 100. And then let's see, when t equals 2, its height is 36. If I can, yeah, there it is. Its height's 36. And at that point, its velocity is negative 64 feet per second. All right, I think that'll do it for this section.